Grateful to Young for giving the presentation. He has already anticipated a lot of concepts, so I can maybe speed up on part of this presentation. Let me see if I can take this on the side. Screen sharing, it's all correct. Yes, okay. So I will also speak about reconstruction of dense velocity data from particle tracks, particle trajectories. And I will also focus on the use of the vorticity transport equation for that purpose. My collaborators, Gabriel Gonzalez, Andrea Shachitano, and Jan Schneiders contributed quite a deal of this work in the past. So I will first give a glance of 3D velocimetry techniques and what is the concept of pouring abundant spatial information in time and pouring temporal information when it's abundant in space, which is indeed the topic for today. And then the transition from cross-correlation to particle-based analysis, that's quite clear, I think, to this audience. And then I'll focus on interpolation of sparse data onto a Cartesian support, a short outline of data assimilation techniques, and then I will give some brief results on time segment assimilation. Let's see. Yes, tomographic PIV starts from the voxels. And so it makes a dense object reconstruction and also gives a dense velocity field by 3D cross-correlation analysis, though that's not very different from planar PIVs in some sense. So the good thing is that you already have the vectors on a Cartesian grid. The bad thing it is that it's quite computationally intensive at reconstruction, at correlation, and in fact, the filtering associated to the window is limiting the spatial resolution. And Matteo Novara went hybridized the concept. He still used voxels to reconstruct the object, but then he focused on detecting particles in 3D, obtaining a sparse particle tracks. And then he was analyzing the velocity vector field on sparse data. The real compression came with the iterative particle reconstruction, so there was no more need to have the domain discretized in individual voxels, but only data was stored when a particle was present. This was, I think, a big step for compression of information. And of course, we all see today, I think in the past 5 years, that Shake the Box has become the state-of-the-art methods. And we have seen today Daniel and his team even further advancing with the time varying algorithms. So the state of the art is that the particles are detected in the 3D space and the trajectory, the kinematics information is also used, and velocity field is reconstructed on a sparse basis. This looks all nice, but it does open the problem to how do we get back to the Cartesian grid? Because many of us need the Cartesian grid to do differentiation, to do all sorts of operations. So let me move further. Yes, when we want to do a dense Cartesian reconstruction, I would rather put questions more than give answers in this talk. So what are the rules that we need to follow for an optimal reconstruction? And I make here a list, but you can add a few more. So the first big question is, how fine should the grid be? And a while ago, thinking with Jan, we ended up with a simple rule that the grid can be as fine as a quarter of the average particle distance. But we see that this is very much algorithm dependent. So a quarter of particle distance could be too redundant, or could be too coarse if you have a very specialized algorithm. So this is still a question that remains there to be addressed. Then which variables can be used from the sparse data? We see mostly velocity being used, but also the acceleration of the particles, so the material derivatives. Then the question that I think will be pertinent for today, shall we use instantaneous data for reconstruction of an instantaneous velocity field? Or can we use, in fact, the history of the particle velocity? And we see that so far, many methods have focused on instantaneous reconstruction, which is nice in general if you have only non-time resolved data, but shake the box in many cases is applied in a time resolved mode, where it gives you the highest data quality. And finally, which governing equations can be used to enforce regularity? We have seen the talk of Dischetti that is more data-driven, and then other approaches are more, say, enforcing physics laws. So these are two different directions. What we know is, if you do a simple exercise, is that if you take a cross-correlation box and you put 5 or 10 particles in it, the wave number, the maximum wave number you can represent for cross-correlation is about 1.5 times the concentration to the power 1/3. And instead, when you move to particle tracking, this is quite boosted, more than a factor 3, almost a factor 4. And this is here a schematic that Jan did to give an impression of what is the typical resolution you get with a linear interpolation. This would be the window size if you are doing a cross-correlation. And then this is the type of data density one could reconstruct if you use the trajectories, velocity, and acceleration. So VIC plus, pretty much what has been discussed in the previous lecture. Let me move further. Data assimilation techniques are used to also to resample data from a sparse support into a Cartesian support, or even from a Cartesian to Cartesian. This was the case of Schiavazzi for imposing mass conservation. Then the vortex in cell based techniques that use momentum and mass budgets. The flow fit uses base functions of B-splines and imposes penalties when mass and momentum are not fully conserved. And what I will speak about is the TSA, Time Segment Assimilation, which is very similar to VIC plus, because it does use the vortex in cell engine to march in time. But the difference is that the vorticity transport is not solved at one time instant or with a little increment, but it is solved during a finite time interval. Now, this is a typical, say, trajectory that comes from STB. We see that how fine the particle position is sampled in time. That's why I talk about pouring time into space. If we see, it's quite a luxury. We have particle positions very close to each other along the trajectory. But then if you look for another trajectory, there could be a lot of space in between. And then the question is, how do we fill up that space? So for the trajectory, typically polynomials are used or other type of appropriate functions. And the typical optimization process is to build a velocity field that is compliant with some physical rules, like the divergence constraint. And this velocity field, however, should be subtracted by the measured data, the ground truth, what we consider, should give a minimum for J. And these type of frameworks have been proposed also in the past in some different variants. So I want to just briefly explain what is the inverse problem and posed with this cost function minimization. And I will explain first for a moment the VIC plus case, and then I will expand into the TSA. So we have a cost function here, J. For the case of VIC plus, I think it was explained nicely before. We consider not only the velocity, but also du dt, the material derivative of the particle velocity. So the particle velocity, particle acceleration. And these two are combined. You need a coefficient alpha first. And second, but not last, the level of noise for the velocity measurement is different than the level of noise from the first derivative, from the time derivative of it. We all know that when you look at the acceleration, that's quite jittery. Instead, when you have the velocity is more coherent in time. So this poses a first challenge in the application of these type of algorithms. And the minimization works by a certain initial condition. Typically, it's just a linear interpolation of the particle velocity, the track's velocity. and then you build a first estimate of J, and by the VIC algorithm, then you will iterate and estimate the gradient of this J, and you will find a minimum there. Now, let's move to, say, the topic of the day. And the main assumption is this, is that the tracer velocity is measured along their trajectory. So we have quite a number of samples along the trajectory. So if you have only 2 frame measurements at the moment, the time segment assimilation is not well thought for that case. So we must have a kind of time resolved data. What is the main idea? The idea is this, that if you take 3 particles in space, P1, P2, P3, and you look at their distance, is this red dashed line, you end up with a certain distance, could be a centimeter. But if you look at the trajectories, gamma 1, gamma 2, and gamma 3, and you look at the distance between trajectories where at the position of the particles, because you don't move along these diagonals, but you go more orthogonal between them, the distance is in fact less. So the distance between trajectories is always less than the distance between the particles. And this is also the case when you don't consider the full trajectories that go, say, from -infinity to +infinity, but you consider a segment of it, just an interval. In this case, the interval is considered here with 5 snapshots. And even in this case, you can see that this distance, the black dashed line, is generally quite smaller, can be made quite smaller than the red line. So the question is the following. Can we say that the final resolution of a method using a finite length of a trajectory will not take into account the distance between particles, but actually the distance between trajectories? If the answer is yes, then we should automatically obtain a method with a higher resolution, because there is less spacing distance between your interrogated point and the surrounding data. Yeah, if the answer is no, it's bad luck. So let me move here. An important point that we have to address is how long should the time segment be? Can it be just 2 exposures, or should it be 2 millions of exposures? And can we identify regimes in these type of time segments? And we have thought about it with Gabriel, and we defined 3 regimes. One is called impulsive sampling. It is a regime whereby the particle tracer is followed over a relatively short distance. So the distance of the track, L track, is typically smaller than the distance between particles. And in this case, because this ratio, the L track over D particle is smaller than 1, then you will not be surprised that the distance between particles is also about the same as the distance between tracks. So it's like the distance on this dark black and what you would have from particle to particle. And so this is, in fact, would give you a result that is similar to just considering a 2-time instance or even VIC+. Then if we take more exposures, actually to a length that is corresponding to the distance between particles, we are getting closer in terms of track's distance. And in this case, the distance between particle is larger than the track distance. So the good news is the inverse of it. So the track distance is getting smaller than the particle distance. And then this is of course advantageous, but we should not forget one thing, is that the information at this position on this track is not taken at the same time as the information at this particle. So the data is non-simultaneous. So the big question mark here is how can we make work together data that is not at the same time, that is non-simultaneous? Can we have a framework that can put together non-simultaneous data for the purpose, for instance, of making a good estimate for a point here? Finally, if we want to overdo it, we can take longer and longer tracks. And I would define these tracks like a bundle of spaghetti, So then we call it stringy tracks, like strings. Oops, the computer is controlling me. So these are stringy tracks. And this means, but what happens in this regime is that still that distance between tracks is smaller than the distance between particles. It has not changed a lot, but what happens is, what has changed a lot is that L track is much larger than distance of particle. So the time span is further enlarged, and the non-simultaneous condition is also enlarged. By the way, the computational cost will also start becoming important. So I think I've said enough about this principle. I will move more quickly to the algorithm. So the large difference, but I think John G has already explained it very clearly. The large difference here is that the input is not a time instant velocity and a time instant acceleration, but is actual velocity at a certain time interval. So all the velocity of the particles over a considered segment that starts at T1 and ends up at the T of the nth exposure. And then the job of this optimization is to obtain a flow event, to compute a flow event in terms of velocity, but because we use the VIC framework in terms of vorticity, that will be fitted to the data through the I move already now to the next one. Yes, so if this is the input, um, the measured velocity at different time instants, and through the vorticity transport equation as governing equation, then we go back to velocity with the Poisson equation, and the cost function in this case has the advantage that it takes a lot of, so multiplies actually the input, the constraints for the solution. And I think a second good news is that you don't have to use the temporal derivative of the particle velocity. So you can stay at particle level only of the particle velocity. So it should be less noisy data, of course, if you don't have outliers. I have limited results here. I'm not advancing as fast, but what is relevant to consider here is first the spatial response. Is it true that this method can improve the spatial resolution? Let's do a test with the sinusoids. And we've chosen a 2.5D sinusoidal input. It is 2.5 in the sense that it is a two-dimensional, so the velocity changes over sinusoids in X and Y, and the Z component of the velocity is non-zero, so it is not really two-dimensional, but it is uniform component. So this is to avoid that the particle would wrap up always on the same trajectory, because this is a numerical case. So what happens is that a method with a good resolution will give you the right value at the peaks and at the valley, and the method with a poor resolution will tend to smear out peaks and valley. Let's see how that worked out. So this is a so-called amplitude response to the sinusoidal input. We know that if we have a sinusoid in our system, in this case, the system is like a top hat filter, then you have still a sinusoid with no phase shift, but with a reduced amplitude. And cross-correlation acts pretty much the same. So this would be for tomographic PIV. So I have imported this type of approach also for method based on sparse data. In this diagram, what do we see? We see one sample sinusoid in two directions. If we use only two exposures, we find out that the method does quite a good job. But in this case, the wavelength is quite large. So as soon as you move to smaller and smaller wavelengths, you see that there is a modulation effect. You don't touch to the maximum and minimum value that would be plus -2, and you can start losing some peaks. And if you start making even larger wavelengths, then, smaller wavelengths, that is a higher wave numbers, you completely lose your alias, or you lose the signal. So what we wanted to see is if we choose a longer time segment, is the situation improved? It looks like it is improved, although there is at some moment also a limit will be touched. If we put all this data into a diagram where on the vertical axis you have the peak velocity, and on the horizontal axis you have the normalized distance between particles, or the normalized window size, Yeah, I think that is it. So what we will see is that if you take a TSA with only 2 or 3 exposures, so similar to VIC plus, you have a certain roll-off. So you go from 100% of the peak up down to 50% at about L star of 0.7. Don't forget that the linear filter would give you that roll-off at about 0.5. So typical for cross correlation. And then if you increase the number of exposure, it looks like the diagram does get flatter and it rolls off later. So in theory, and even with this numerical exercise, even with its limitation, it looks like that a better resolution can be achieved. There is some overshooting here that one should pay some attention, an overshooting of about 5 to 8%, and that we have to understand where that overshooting is coming from. So in some cases, the peaks are even larger than the physical value, but I would not bother too much for 5% overshooting when we get 50% of modulation. I have a simple 2 slides only for an example, a cylinder wake experiment. I've seen a lot of numerical data, and things go quite nice with the numerical data. In experiments, the things start wrong from the beginning. So the cameras or the illumination is not ideal. The imaging is not ideal. We use here helium filled sow bubbles, so they give glare points, so 2 points per particle. This is also problematic. So this is a relatively large scale experiment. If you see, the field of view is approximately, I might say, almost is 0.5 meter by 0.5 meter by 0.5 meter. So it's huge. The cylinder itself is 10 centimeter and 2 meter long, set in a wind tunnel with a 3 meter by 3 meter exit test section. The velocity is a low velocity to help having time resolved information by these 3 photon cameras. We used LED modules. They were enough to give enough light, and acquired the 2 kilohertz. So we used the shake the box from Davis, and the PPP would be like an optimal PPP, like 0.05. But actually, so far we could get, I made a typo here, my mistake. We get only 1/10 of that. So we get only 5,000 tracks out of the 40, 50,000 particles detected. So probably we still need to tune better the parameter of the algorithm to get all the particles in the images. Yeah, this is a snapshot I took with a camera on the screen of the computer. So you can see this tracks is a very nice coherent Kármán wake. Blue and red is a velocity that goes up and down. And we have been quite selective of the tracks only with the 9 exposures or more in order to make sure that the number of outliers would not pollute too much the result. When, then I have just a sample here of a result. And this is just to show that when you take a simple interpolator, you do get the Kármán wake. And you also get some filaments known as the ribs that leave across these large Kármán vortices. And when the TSA method, in this case with the 11 exposure, is chosen, we recover 1 vortex even that is weaker, closer to the cylinder, so at its formation. And the ribs are somewhat more evident, but we see a lot of other features, say bubbles, that we have to look after to see if the method is not too sensitive to noise. Let me conclude. I see Benjamin appearing. Okay, the conclusion is that time segment assimilation based on the VIC is a principle based on a flow event rather than on a flow time instant. It does increase the basis of the measured data that bounds the solution. And the algorithm is an optimization of a cost function based only on velocity. The spatial response indicates that there is a potential. There is some features, the amplified response at a normalized wave number needs to be looked after. But bottleneck is that moment takes forever. It's extremely time consuming. And certainly we have to move at least towards a marching approach, maybe following indeed the shake the box philosophy that marches in time. And further work is to reconstruct not a snapshot, but even the full segment, and use the full segment. That will further accelerate the data. But it looks like that an implementation, already convincing one from John G, has already been made of this method. So I'm quite positive for the future. Thank you for the attention. That's all.
Thank you very much for this very nice and very clear talk. I see there have been some debates about the first TOMO-PTV attempts, but I suggest that we take it has been solved since. So let's switch to question. Dominique?
Yeah, thank you. I have a question concerning the length of the time segment compared to the typical time scale of your flow. For instance, for the last case, how long can you consider your time segment compared to the vortexing periodicity?
Well, good question. Thank you. As you see, I was flying a little bit at the lower level. I said the length at this moment could be considered when I gave you this example. If I'm allowed to go back here. Yeah, for the purpose of obtaining an advantage, the length of the segment should be longer than the distance between particles. Otherwise, no real advantage is to be expected. So we would need to go at least in this condition. Now, if there are flow features that occur in between the distance between two particles, yeah, then it's a really good question there on how can you represent them. I would say that let me make a simple answer. The time scale of your segment is not bound to be shorter than the time scale in the flow, because we march the flow in that time interval with the vorticity equation, which is actually the governing equation for the flow evolution. So if there is an event happening in that segment, it's not just a linear fit that is straightening everything, is the vorticity equation. So it will, for instance, predict vortex stretching or vortex tilting. I would look at particle distance. Imagine it's 1 centimeter. Then I would look at the general convection velocity, 1 meter per second. And then I would allow length such that the particles, so the integration is at least 1 centimeter based on convection. Is this an acceptable answer?
Yes, yes, of course. Thank you.
Okay.
And maybe an additional question, due to the length of your integration, did you see any divergence of your advection model?
No, divergence not. Strange enough, disappointing enough, what we see is that when you integrate the flow, as in fact for almost any numerical simulation, in our case, given the choice of the grid, that is still a kind of a greedy grid. We don't go for 1 million points. Then the solution tends to diffuse. Yeah, so it tends to become more diffuse. So you tend to lose details. So you do get convection. You do also get some effect of the vorticity transport, but you don't really conserve all these small ripples of vorticity. It tends to diffuse a bit. I think it should be looked after. So the solution is less good when you go away from the central point.
Thank you very much.
You're welcome.
We have time maybe for one quick last question, if any. I have one. Do you already account for the fact that your data could have some noise? And if not, do you have plans for that?
What do you think? So the data has noise, and I try to account for it. I would say a la chance, in the sense that I try to use the parameters of the shake the box in a way that I don't get at least the wrong tracks.
Okay.
To be honest, no. The method is not accounting in an explicit sense for the presence of outliers. Implicitly, however, because you take you take a finite time segment that will also contain maybe compensating component of noise because of the time span.
Can you hear me now? Okay, okay.
No,
So I need to admit the participant. How do you do that?
Excuse me, Jean, can you please switch your mic off?
Oh.
okay. So Benjamin, no, I think it's still the good old story.
Admit.
We would like to have data as clean as possible. And in my impression, it looks like better, less data, but clean than more, and with all these seeds of crap.
Okay, thank you very much again. It's time now to switch to the last speaker of the day. So this will be Sebastian Gesemann.